A physicist is happy when an experiment goes wrong. An engineer not so much. But both really want to know what it is that went wrong. How to analyze that is the topic of this video. Ideally, our modeling diagram commutes, and modeling plus calculating is observing, or if you're an engineer, calculating equals implementing plus observing. So your design works as expected. But whenever this is not the case, there may be multiple causes for this. After all, measurement equipment is not perfect, so something could be wrong in the observations arrow. Human thinking is not perfect, so there may be something wrong in the modeling arrow, or there may be something wrong in the implementation arrow. And calculations may sometimes be approximations as well, since we do not have infinitely many digits on our calculators, so there may be something wrong in the calculation arrow. Without anything further to compare with, it's impossible to tell which arrow contains the mistake. But the nice part of having both a syntactic and a semantic model is that we have other arrows to compare to. In this video, I do not give you answers on how to find mistakes, but I do suggest a number of questions you should ask yourself when you're debugging your model in your engineering work. To catch a mistake in your calculations, you may want to compare your calculation to its semantic definition. So you want to see if calculating equals formalizing plus defining. In practice, you do this when you make calculations that are actually approximations, if you don't have enough digits, or if you know that the outcome of your calculation is actually a limit of something that you have to approximate rather than you can calculate it precisely. When the outcome of a calculation provides an answer that is roughly in the range of its theoretical definition, then we say your model is accurate. Furthermore, when the error range is small, we say the model is precise. For a model to be useful, it needs of course to be both accurate and precise. The most common error to make is to mix up the two. But precision means that every time you do the calculation, you get approximately the same answer, there's little variation, while accuracy means that the answer is indeed close to the answer that you want. To catch a measurement mistake, you compare the outcome of your measurements with your intuition on what the outcome should be. So you compare observation with meaning and definition. But often the mistake is not so much in the understanding of what should be observed, but rather in the practical possibilities for making observations. In other words, we are not exactly able to implement what we intend to measure. In such cases, there is a mismatch between the formal definition of the measurement and its actual implementation. So formalizing is not equal to implementing plus meaning. A different way of looking at that would be to state that the modeling itself is inadequate. So modeling plus formalizing is not the same as meaning. This error is arguably the most abstract of the three, because you're both involving the real world, which is something that we cannot reason about precisely because we don't really know it, and the semantic model, which only exists in our mind. Many theoretical courses focus on this aspect of the modeling diagram, since it emphasizes how things should work out in theory, while the more applied courses often focus on calculation and measurement errors, as those are the things that actually go wrong in practice when you're actually trying to implement or do things, after the theoretical work has already been done. A nice property of the modeling diagram is that the errors that we make between the different arrows can be added up. And in this way, we see that the prediction error is always smaller than, well, the prediction error is defined as the difference between observing and modeling plus calculating, but that is smaller than the distance between observing and meaning plus defining, and the distance between meaning plus defining and modeling plus calculating. And that in turn is smaller than the distance between observing and meaning plus defining, and calculating and formalizing and defining, and meaning and modeling and formalizing. The three add up. So the prediction error is smaller than the measurement error, plus the calculation error, plus the modeling error. In a similar way, you can say that the experiment error, the difference between calculating and implementing plus observing, is smaller than the calculation error plus the measurement error plus the implementation error. What often happens in computer science is that we have either a modeling error or an implementation error, and we find it by doing more measurements, by extending our observation error. Because in computer science, it's rather easy to implement new observations by extending the logging. So you can actually use your control over one of these arrows to find errors in the other ones. That is called debugging. So whenever you find a discrepancy between your modeling and what happens in the real world, realize that it could be 4 different types of errors. It could be a modeling error or an implementation error. It could be a calculation error, or it could be a measurement error. It could be that your modeling is inadequate, or it could be that your calculations are either inaccurate or imprecise. And it could be that your measurements are just off, that you're not measuring what you intended to measure. Whenever you're reporting about this, use these words carefully so that your audience understands what kind of error they are dealing with, or you are dealing with. The same holds when you're dealing with 2 different models, not with a model and the real world, but with the difference between 2 different models. And if there's a discrepancy between those, that may be because the 2 models have a different semantics than you thought, or that may be because one model has a calculation error that the other model has not, or that the definitions are slightly off. So you can also use this diagram to figure out discrepancies when you have a mistake between 2 different models. Finally, one thing that I did not talk about is estimation errors. Of course, that's also a source of mistakes that you can make in this diagram. I'll leave it to you to figure out how that actually works out. Just stare at it a little longer.